Hello and welcome to the MOOC on optical communications. In this module we will give a brief introduction to system design of optical fiber communication systems. Of course, we still do not know much about various components of optical systems and how they will influence the overall system, but this attempt of system design, which I have characterized as system design 1, is to essentially talk about two important effects. We will modify the complexity of the problem as and when we talk about other components and other parts of the system throughout the course, but for now let me introduce you to two topics which come up in system design, and whatever we have learned so far is sufficient for us to design a simple working optical fiber communication system. Okay. So, with that in mind, system designers are typically interested in two quantities. One is called as the power budget and the other is called as the rise time budget. Now, power budget in its very simple sense is essentially budgeting the total power. So, let us say I have a receiver that usually is fixed, having a certain sensitivity. Sensitivity in our case can be thought of as what is the minimum optical power that the optical receiver requires so that it can detect optical signals. So, if that is assumed to be fixed, right, then the question that power budget designers are looking at is what would be the minimum transmit power that is required so as to cover a given length. On the other hand, if someone has an ability of the power, then one can talk about what would be the maximum length over which we can communicate. So, these are interrelated quantities. So, you use a larger power, you can go longer distance, but increasing larger power brings with it lot of problems which we are not considering at this point, we will consider them later. Okay. So, for now you can consider that increasing the optical power makes the length of the fiber increase. Of course, it is not just an optical source, a fiber and an optical receiver that forms an optical communication system. There are additional components. The optical source would be a laser or an LED for a cheap and a simple and low transmission distance system, but for long haul systems it is a laser. So, you have a laser emitting light. This light has to be coupled into the connector, into the fiber. Okay. So, there has to be a laser to fiber coupler. Okay. And sometimes this comes in with a package. So, you have a laser diode, actually most of the time it comes with a package. So, you have a laser diode emitting light, there is a micro lens which focuses light onto a pigtail of the fiber. So, we call this as a fiber pigtail, which then completes the laser diode. That is to say, the optical source comes with a laser diode, a lens and a fiber. We are now connecting that fiber to the modulator, or you are connecting that fiber to the actual transmission fiber. So, when you have to connect two fibers, you have to use what is called as a connector. We will see some types of connectors later as we talk about them, but for now connector simply means I can connect light from one to other. Okay. Then I have the transmission fiber through which the signal propagates. As we know, the fiber gives some loss, or rather the fiber induces loss in the signal that is propagating. So, the power keeps going down. At the output end, you have to connect again light to the optical receiver via one more connector. In between, you might have to also do something called as splicing up. So, splicing means that you are taking two optical fibers, but you are not putting them through a connector, but rather fusing their cores together. This process is a low loss process, and that is used for to couple many other components along the way. So, the point here is that you start with the transmitter, then as you go until the receiver, up to the receiver, you will see various components, you will encounter various components, each of those components are going to give you loss. So, after the total loss, if you calculate what is the total loss, then whatever the power that you receive at the receiver will be the power that you have to use in order to recover the data. Now, the question is, I have a receiver with a certain sensitivity, of course, which means that my received power should be at least equal to the receiver sensitivity. In many cases, I cannot operate it with such a constraint. I actually have to keep my received power at a slightly higher value compared to the sensitivity of the receiver. The reason why I have to do this is that many optical components change during the course of operation, they undergo aging effects, they slowly deteriorate, the values drift. So, all these things will contribute to additional losses, which if the system designer does not think ahead, then operating it with such zero margin would lead us to a problem. Any small change in the optical link will simply mean that the link becomes unusable. So, if you have to cope with reasonable number of failures, then you have to keep the received power at a slightly higher value compared to the received optical power. In addition to this, sometimes the system designer has to take into effect the future upgradability of the optical link. So, let us say I want to include a WDM router later on, not today, but maybe once the traffic increases, then I want to include a WDM router. Maybe I also want to include a WDM multiplexer, maybe a demultiplexer, maybe a filter. So, I can include all these components, but each of those components that I include in the link will give rise to more losses. So, if I do not plan ahead, so what are these losses that might happen for the future upgrade, then I will not be able to use the link later on. So, power budget is a very simple task, seems to be a very simple task, okay, but it involves lot of intricate details. Okay. For now, we will consider a simplified power budget analysis. What we do is we assume that the goal of us is to either calculate what is the minimum launch power or P in, as we will denote that one, and also calculate what would be the length of the fiber. Okay. So, the receiver minimum sensitivity is something that is known. This is mostly determined by whether we are looking at the analog transmission or digital transmission. If it is digital transmission, we are looking at what bit error rate we are operating in. Okay. The lower the bit error rate, the sensitivity actually goes up. So, if you want an operation at 10 to the power minus 9, the receiver sensitivity might be around minus 37 dBm, okay, for a given bit rate. However, if I want to operate with a bit error rate of 10 to the power minus 12, then my received power actually goes up. In other words, the minimum received optical power goes up. Okay. So, it is a quantity that depends on the what BR is required. It also depends on what is the bit rate of the system. Okay. For now, we will not worry about who calculates this sensitivity. We will simply assume that this is known to us. Okay. So, this is known to us and we are going to work with this sensitivity. Okay. For analog, the performance is characterized in terms of the signal to noise ratio, or sometimes it is characterized by the signal to distortion ratio. Okay. But we are not going to consider analog systems at this point, we will simply concentrate on digital optical links. Okay. Now, here in this table I have shown couple of optical elements. Okay. We have a connector whose loss in dB is actually a range of 0.5 to 1 dB. 1 dB is typical, 0.5 dB is with very good connectors. Fiber losses at 1550 nanometer, this again is a variable for the system designer. You have to choose which wavelength window that you are going to operate. So, that loss is 0.2 dB per kilometer. The splice loss, as I mentioned, will be around 0.5 dB for each splice. So, if you increase the number of splices, then the total splice loss also goes up. Now, what is the power budget, right? So, in addition to this, we might also write down what would be the system margin, which is the upgrade margin that you are looking for. Let us call this as about 6 dB, okay, and let us also call this excess margin, which incorporates system link failures, aging, drift, all these problems which induce losses. So, let us call this excess margin as 3 dB. Now, the question is, pick a value of P in and pick a value of L such that you are able to operate this particular digital link. Okay. So, in order to do that one, I need to tell you what is the sensitivity of the receiver. Assume that for a 10 to the power minus 9 BER that we are looking for, the receiver sensitivity is minus 37 dBm. Okay. And then you have all these other margins given. What you have to find out is P in as well as L. How would the loss vary? Graphically, you can see that at this point I am starting with some launch power P in, which I will measure in dBm. Remember, losses are better talked about in dB scale rather than in the linear scale. So, let us say I convert whatever the input launch power in the linear scale in the watts, milliwatts to dBm, and I start with that. The first loss that I encounter will be the connector loss. Correct. So, I will first encounter the connector loss, therefore, the power at this point would drop from P in to P in minus alpha C0. So, this is the launch power into the fiber but it has to be connected. This launch power coming from the transmitter has to be connected to the fiber by a connector. So, connector will induce a loss of alpha CO. So, the power drops to P in minus alpha C0. At this point the power actually starts decaying because the fiber introduces a loss, and at the end of the transmission over a length L, the total loss in the fiber is alpha F into L. Therefore, the power at this point will be P in minus alpha CO minus alpha F into L. Alpha F is measured in dB per kilometer and L is measured in kilometer. Okay. Now, what happens next? I might actually have another connector here, okay, which causes my optical power to drop down to P in minus 2 alpha C0, 2 because you have 2 connectors here. The more the number of connectors, the more the points that you have to include, minus alpha F into L. Okay. You might also encounter a certain splice in between, okay, at which point your power would have dropped and then again decreases. Okay. So, this would be the splice loss. So, let us assume that there is only one splice in this particular scenario, and that would be minus alpha S. This is the power that you are receiving. Okay. This is the power that is receiving, but we want to consider a system margin of 6 dB and an excess margin of 3 dB. What it means is that if this is my PRX min, which is the minimum received optical power, then the optical power that I receive here must be above 6 plus 3, which is equal to 9 dB. So, in other words, if this link completely fails, giving you a loss of 6 dB with respect to system failure, and if the drift, aging and everything happens, there will be additional loss of 3 dB. So, this 6 plus 3 is equal to 9 dB loss will come into picture when either the link completely fails or you are going to get excess margin as well, right. So, your components all drifted and then you got a pretty bad components that you are working with. So, this is the received power. Minus 9 dB would be the power that would be at the edge over which we are operating the received optical power. If you want, you can actually keep the total received power to be greater than received minimum received power. Okay. After considering the margins, you might still have an excess margin of about 1 or 2 dB. It is typical to do so. Let us assume in this case that we are not going to use any excess margin over and top of the margin that we have already specified. Okay. So, my goal would be to try and make the total power that I am receiving, including the margin losses, to go to PRX minimum. So, the equation is very simple. PRX minimum will be equal to, this is the optical power that is required, minimum optical power required for the detection of the optical signals. This is equal to launch power minus total losses in the system. Losses come from 2 alpha C0, which you will have to replace it by n alpha C0 if you have n connectors. If you have 2 connectors, is 2 alpha C0 minus alpha F into L, which is the fiber losses, minus alpha S. Replace this minus alpha S by n into alpha S if you have n number of splices, minus margin, which I am calling it as M. Okay. This should be equal to the received optical power. So, substituting this for our case in the above situation, what we get is P in is a value which I do not know, alpha connector loss, let us take it to be 1 dB. So, this would be 1 into 2, that would be 2, minus alpha F into L is 0.2 into L, I do not know what is the length of the propagation, right. So, I have to find that one out, minus assuming one splice loss is about 0.5 dB minus a margin of 9. Okay. So, this received power must be minus 37 dBm. So, you can look at this equation. So, you actually have P in minus 0.2 L is equal to minus 37 plus 2 plus 9 plus 0.5, which turns out to be minus 37 plus 2 is minus 35, minus 35 plus 9, this is about minus 24. So, it is about 9 and 1, which is 10. So, minus 27, minus 26 and minus 25.5. Okay. So, this would be the power that you are looking at. This equation is what you are looking at. Now, it is interesting, I actually have 2 variables. Okay, so I can rearrange the variable slightly. I can rearrange it in this way. Let me write this as, so I will rewrite this as P in is equal to minus 25.5 plus 0.2 into L. Okay. Now I will plot L versus P in. If I want to propagate a certain distance L, what should be my P in? Of course, with L equal to 0, which is the case where there is no fiber, then P in can be at minus 25.5. Let us put all this in dBm, right, and then from here onwards it would be a straight line. At some point you will see that the power or the P in will be equal to 0 dBm, and that will happen when you are looking at 25.5 divided by 0.2, and this would be the graph that you are going to look at. Okay. Now this graph is for a 1550 nanometer operating window. Here is an exercise which you can use, you can actually write a small MATLAB program to compute this one. Exercise is that consider the losses for a 850 nanometer fiber and a 1300 nanometer fiber. These values can be obtained from your textbook. Find these values, substitute into these equations. Okay. So what quantity will change? This quantity will change, right. This would not be 0.2, but rather it would be the value that corresponds to 850 nanometer or 1300 nanometer. Okay. And this times L should be equal to this. So calculate on the same graph, right, plot on the same graph the curves corresponding to P in versus L. Okay. So this is a simple exercise that you can choose, and then you can see that if you either fix P in, you can find the corresponding value of L, or if you fix L, you can find the corresponding value of P in. So this completes our discussion of power budget. Now let us look at what is called as the rise time budget. Okay. So in the rise time budget, what I am looking at is the effect of dispersion. Okay. So I know what is the main effect of dispersion. Dispersion simply causes the pulse to spread out, right. So if I am performing digital modulation, then I can perform modulation of the information on its amplitude or amplitude and phase, which is the quadrature amplitude modulation that we talked about. For now we will assume only on off keying type of modulation, which is also the amplitude shift keying modulation. Okay. Here I can actually transmit pulses in two different ways. One is called as the RZ transmission, the other is called as the NRZ transmission. RZ stands for return to 0. Here a bit 1 is considered, bit 1 is represented by a pulse which lasts for about half the period. Okay. Whereas for the NRZ case, the bit 1 is represented by a full width pulse. Okay. So the pulse lasts all the way up to t seconds. For 0 you transmit nothing over the bit period. Similarly for 0 you transmit nothing over the bit period. For the NRZ case, if the bit rate is B, okay, then the bandwidth requirement for the NRZ case is equal to B by 2, whereas the bandwidth requirement for the RZ case is equal to B, and typically B is 1 by T, where T is the pulse width and B is the bit rate. So you are sending one pulse every t seconds, and that corresponds to a bit rate of B, and the bandwidth requirement is B by 2 for NRZ, and for RZ it is B. You can see why this is so if you look at the NRZ transmission for bit sequence 101010. This is where you get the maximum change of amplitude, right. So for 1 will be duration of t seconds, 0 is here, t seconds. So this is 1, this is 0, this is 1, this is 0. This duration is t seconds. Whereas for the RZ case, you have maximum transmission, I mean the maximum change of bits when you have transmitting all ones, because when you transmit all ones, you have one half period, then one more half period, then one more half period, another half period, and so on, right. So this would be your total width t, whereas this one is only about t by 2. Okay. So the fundamental period here is 2t, the fundamental period here is t, therefore the bandwidth requirement is 1 by 2t or b by 2, whereas the bandwidth requirement for the RZ case is 1 by t or b. Okay. So if I am looking at 2.5 Gbps transmission for NRZ, the bandwidth requirement is 1.25 gigahertz, for RZ it would be 2.5 gigahertz. These are quite rough values. A different way of expressing the same information is to talk about the rise time. Okay. A rise time for a signal is specified by looking at its 10% to 90% of the final value transition. What is the time required for 10% to 90% transmission, and this is called as the rise time of the pulse. Okay. For NRZ this is about 0.7 by B, this is for the NRZ case, and for the RZ case this is only about half the time, okay, because RZ pulses have to rise up because they also have to fall down, right. In the half period they have to rise and then they have to fall, whereas for an NRZ case it has to rise and then it has to fall at a much later time compared to RZ. Now, which kind of modulation technique that you are going to use? Will you use RZ or will you use NRZ? The answer to this question depends on various factors. With RZ scheme it is kind of easier to obtain the clock, which means I can synchronize them even if I am transmitting a sequence of ones. It of course does not work when I transmit a sequence of zeros, but neither the NRZ scheme will work at that point. So, for RZ scheme if you are transmitting a bit of a string of ones, it is still possible to recover the clock. Okay. For NRZ scheme it is not possible, or it is very difficult, because for continuous ones the power will be continuously on, there are no boundaries that you can easily detect. Well, if you are looking for bandwidth occupancy, NRZ occupies smaller bandwidth because its period is larger, time period is larger, whereas RZ occupies a larger bandwidth because its time period is smaller. So, if you are looking for bandwidth conservation, NRZ is the thing to go for. Okay. If you are looking at dispersion combating, then NRZ is bad because the signal occupies the whole period, and once dispersion kicks in then the pulse will actually deteriorate and then cause intersymbol interferences. So, NRZ is not a very good option there, whereas RZ, since it occupies only half the time slot, even if it expands a little bit, no problem, it can in fact expand for another half period before or rather 25% of the period. So, it does not really matter to us because RZ still will remain within the time period, whereas NRZ would exceed its time slots. Okay. In case you are looking at nonlinear effects in the fiber, something that we are going to discuss later, then NRZ is bad because you are now transmitting full optical power for the entire duration. However, RZ is even more worse because RZ corresponds to transmitting pulses, and within pulses the peak power increases, which will then cause higher nonlinear effects. So, there are a lot of factors which are involved whether you are transmitting NRZ or RZ, but for this we are interested in knowing what is the rise time requirements. Okay. So, my overall system rise time must be less than this quantity, it has to be less than 0.7 by B for NRZ, it has to be less than 0.35 B for RZ. Okay. So, let us see what and how we can look at. Rise time in optical communication systems is given by three factors. So, there is the total rise time, let us write down, which we call as the system rise time. This is given by tau t square, which is the transmit rise time. This quantity is not very important in modern optical communication systems. About 10 to 15 years ago, this was important because your lasers were directly modulated. Today you use an external modulator as we discussed. So, this quantity is not very important except for the legacy systems, and then you have receiver rise time, which is very important because this is directly coming from the photodetector. So, if you do not have a high speed photodetector, then it simply will not respond to your signals. Okay. You might send in a nice rectangular pulse, but if the photodetector bandwidth is very bad and very small, then you will get a signal which is like this, which is very distorted and you will not be able to measure anything. Okay. So, photodetector rise time is important, but more or less the limitation comes from the fiber rise time. Okay. So, fiber rise time is denoted by tau f square, and this fiber rise time is actually dependent on this fiber rise time is basically the pulse spreading, which depends on the dispersion coefficient d delta lambda into L. This is for the case of single mode fibers. For multi-mode fibers you have to consider the intermodal delay, which is the main limiting factor. Anyway, we will not consider multi-mode delay. For us single mode fibers are more than sufficient. So, for single mode fibers the pulse spreading is given by d into delta lambda into L. So, you can substitute that into this expression. Okay. Let us consider a typical example. and then see what happens. Okay. So, let us consider the typical example in which my data rate RB is about 400 Mbps and I want to transmit over 100 kilometer. My transmitter rise time is 1 nanosecond, my receiver rise time is something that I have to calculate. Fiber dispersion for a single mode fiber is given by 17 picosecond per nanometer kilometer if I am working at 1550 nanometer with a zero dispersion wavelength of the fiber at 1300 nanometer. Remember we talked about in the previous module. However, this goes down to 2 picosecond per nanometer kilometer if I am working with the same 1550 nanometer operation, but zero dispersion wavelength has been shifted to 1500 nanometer. This fiber is called as the dispersion shifted fiber, this fiber is called as the standard single mode fiber. Okay. So, this is the standard single mode fiber and this is dispersion shifted fiber. So, depending on these two you can satisfy the overall rise time. Let us now look at it. Suppose I consider the standard single mode fiber, okay. Then the pulse spreading comes out to be D is 17 picosecond per nanometer kilometer, my length is around 100 kilometer. Okay. What about the spectral width? If I am using an FP laser, that is a DFB laser, but it is having multiple frequencies, which is, if I am using a laser with multiple frequencies, this is called as FP laser, Fabry-Perot laser. This laser has a spectral width of about 4 nanometers, anywhere from 1 to 4, and modern FP lasers have about 2 nanometer, 1 to 2 nanometer. This is a slightly older design, so it has a 4 nanometer spectral width, okay, delta lambda. Whereas a single frequency laser or a DFB laser has a width of about only 0.2 nanometer delta lambda. Okay. So, if I first operate with the FP laser, which corresponds to 4 nanometer, this will be around 6.8 nanoseconds, whereas the same value will be at 17 into 100 into 0.2. So, this value is about 0.34 nanosecond, not 3.4 nanosecond. So, clearly the spreading due to the fiber is less here, but what is the maximum allowed system rise time? I mean, so maximum allowed system rise time basically comes from the bit rate. So, we have seen that the bit rate RB is 400 megabits per second. So, if you calculate what would be the system rise time, assuming that we are looking at NRZ. So, NRZ we have seen that this should be 0.7 divided by RB, which is, if you put in the values of 400 Mbps, this turns out to be 1.75 nanoseconds. Okay. 1 nanosecond is already coming from the transmitter. So, if you look at the fiber for two cases, okay, for the 6.8 nanosecond we are hopeless, because I cannot in any way reduce 6.98 nanosecond, and on top of it I am going to add some rise time for the receiver and for the transmitter. I will never be able to reach this 1.75 nanosecond. However, if I operate with a dispersion shifted fiber, the pulse spreading because of the fiber itself is very small. So, in this case, if you calculate what is the receiver rise time, which is given by square root of tau NRZ square minus tau f square minus tau transmitter square. So, you can substitute all these values, it will turn out to be 1.42 nanosecond. Okay. So, the receiver rise time is around 1.42 nanosecond, which is much smaller than 1.75 nanosecond. So, in this way you have to design the components in such a way that you are actually transmitting signals at a given bit rate with the overall goal of maintaining the rise time budget as well as maintaining the power budget. For different fibers, for different operating conditions, this budget, rise time budget will also change, and you can use MATLAB in order to calculate all these values. Okay. So, we will supply you with a small MATLAB program which you will be able to use in order to come up with the maximum value for propagation distance and for the rise time of the system. Thank you very much.